Alright, my friends, the time has come in this section 5.3 when we're looking at polynomial graphs. You will not be able to use your calculator in this section or on the mastery check. So it's time to get down and dirty with some of these polynomial graphs and actually analyze the functions to help us determine what their graphs are going to look like. So we're not going to be using our calculators, we're going to be using the old-fashioned ones called our brains. So do me a favor, if you have your calculator out right now, okay, it might be a little tempting, but please put it away. We're going to try to do this the old-fashioned way by just looking at equations. So speaking of polynomial graphs, we've been looking at polynomial equations so far in this unit, but today we're going to be focusing on their graphs. Polynomial graphs, there are three specific things that we know about these types of graphs. There will be no discontinuities, so we're going to have these smooth curve-like graphs. You can think about this cubic graph right here, you can think about a quadratic, a parabola graph, but there will be no discontinuities, no holes, no asymptotes, no jumps. You can draw all of these without picking up your pencil. The other thing is that there are no sharp corners. So unlike an absolute value where we have this V shape going on, we have this sharp corner somewhere right there. All of the corners, I guess you could say, in our polynomial graphs are smooth. So you can kind of almost think about these polynomial graphs as roller coasters, where we have this gradual hill or slope even at the top or at the bottom. There are no sharp corners that these roller coasters would be going over. So they're always going to be smooth curves. There's not going to be any sharp corners. And the domain is very nice for all these polynomial graphs. They're always going to be all real numbers. So you can pick any x value you want to plug into these polynomial equations and you should get a y value out. So all real numbers, really nice domain for polynomial graphs. Some common graphs that we should already know about, for instance, are linear graphs where we have this line. Remember the parent function for that is just x. Quadratic graphs, we know they look like a parabola. We might have a U shape, and the parent graph for those are y squareds. Cubics, they might look something like this. They also might have some humps or bumps going around, almost like the one we have in our example up here. So cubics can take different shapes. They might have different amount of turning points. We're going to talk about those in this unit. But the parent function for those is always x to the third. And a quartic, kind of the same thing going on with cubic. We might have a very wide parabola, very similar to a quadratic, but quartic graphs can also have some turning points. For instance, they might look something like this, where they have kind of these three humps going on instead of the two humps like the cubic has. And the parent graph for those are x to the fourths. So we have these common graphs of polynomial functions that we're going to be analyzing today and graphing without a calculator. Alright, so the first thing we're going to talk about in order to help us graph these polynomial functions by hand is the end behavior. Now, we've been talking about this so far this year. End behavior, remember, is what's happening literally at the far ends of our graph. So what's our graph doing on the left-hand side? What's it doing on the right-hand side? These end behaviors are the limits of our function as we go off towards negative infinity and positive infinity, all the way out to the left and all the way out to the right. So is our graph going up? Is it going down? Or is it kind of leveling off at some horizontal asymptote? And depending on what our polynomial graph actually looks like, we should be able to determine what the end behavior actually is. We're going to look at two specific things in our polynomial function to help us determine the end behavior. The first thing is whether our leading coefficient, okay, that number kind of written out front when it's in standard form, is that number positive or negative? So that's going to tell us something about the end behavior. But we're also going to look at the degree. Is our highest exponent even or odd? That's telling us something about the end behavior as well. So if we think about a polynomial graph that has a positive leading coefficient as well as an even degree, okay, for our little example, maybe that would be a quadratic x squared. Okay, so notice how this is positive. Okay, we could think about a little +1 in front of that. Okay, it's a positive x squared, and it's an even degree. We have that power of 2. And we know that x squared graphs, these quadratic graphs, look like parabolas. So in this instance, we're going to have a graph that looks like this. But remember, the x to the fourths, if I go back for a second, Notice how the quartic graphs, these x to the fourths, kind of look the same way, but they might have a few humps in the middle. So I don't really want you to draw this smooth like this. I'm going to say there might be some humps in here, but the main idea is notice how on the left end of the graph it goes up, and on the right end of the graph it goes up as well. Regardless if we're dealing with a power of 2 or a power of 4, both ends of the graph are going towards positive infinity. So our left end behavior, the left-hand side of our graph, is going towards positive infinity, and the right end behavior, this piece of our graph, is going towards positive infinity as well. But if we think about the negative leading coefficient, maybe we'll have a negative x squared. We know that simply turns our graph upside down. So we're going to flip it. We have that reflection. But again, we're not really sure what's going on in the middle. We might have a few humps and bumps. So we might have those little pieces in there. But again, notice how the end behavior just kind of switches. This time the end behavior, the left-hand piece, is going down. So this would be a negative infinity end behavior. And so is the right-hand piece. So this would be going down as well. So depending on if you have an even degree and it's positive, we're going up and up, okay, both towards positive infinity. But if we flip it, if we make it negative, notice how they both go down, negative infinity and negative infinity. So let's move on to the odd degrees. Maybe in this case, instead of looking at an x squared, we'll look at an x to the third. We know that this graph kind of looks like this. But again, we might have a few humps and bumps in there, just like in this example here, we had a few humps. So we're going to throw in a few humps, but the main idea is that we're going down on the left-hand side. Okay, so the left end behavior would be going down towards negative infinity, but the right-hand side is going up towards positive infinity. So kind of similar to this one, it's just that the left piece, since it's an odd degree, is now going down. Now if we flip it, if we think about a negative leading coefficient, just putting a little negative sign out front, sometimes you might have a -2, okay, we might have that vertical stretch going on, but the main idea is that it's negative. So that's going to flip our graph, it's going to reflect it, it's going to look something like this now. And again, we might have some humps and bumps in the middle, we're not sure, but the main idea is that now, since it's flipped, it's negative, the left side is now going up, so this is a positive infinity, and the right-hand side is now going down, so the right end behavior would be negative infinity. So just by analyzing the equation, okay, looking at what is that first leading coefficient, is it positive or negative, and what is the degree, is it even or odd, we can determine what's going on at the ends of our graph. Are they both going up? Are they both going down? Is the left-hand side going down and the right-hand side's going up? Or is the left-hand side going up and the right-hand side going down? Alright, so two more things that we're going to be able to find or determine based on our equation is the number of turning points or extrema, those maxes or mins we have, as well as the zeros of our equation, okay, in other words, those x-intercepts. So in terms of turning points, a polynomial of degree n, okay, so the highest degree we have, is at most n minus 1 turning points. So just as an example, I know words can kind of get confusing, we'll take a look at an example here. Let's just say that our polynomial degree is a quadratic. We have this x squared. There might be some other pieces in here, maybe like plus 2x minus 1. These might change, but the main idea is that we have a degree of 2 in this case. So that tells us that if our degree is 2, then we have 2 minus 1 turning points, or in other words, we just have one turning point. I'm going to abbreviate it TP. And that makes sense because if we think about a quadratic, it's either going up like this, or it's going down if it's negative. And here's our turning point. There's our extrema. In this case, we would have a low point, and in this one, we would have a high point. But overall, that's just one turning point. This is one turning point, and this is one turning point. But if we had a cubic, for instance, if we had an x to the third, that means we can have at most 2 turning points. because if we were to take a look at our degree of 3, 3 minus 1 would give us 2. So we could have a normal quadrant, or a cubic in this case, where we really don't have any. Notice how I'm just keep going up in every case. I don't have that turning point, those extrema. But we could have a cubic that has those little humps or bumps in the middle. So here's a turning point, and here's a turning point. We would have those would be relative extremas, but they are turning points. We go from increasing to decreasing, but then in this piece we would go from decreasing to increasing. So this little degree is telling us how many turning points we have at most. Okay, we could always have less, but at most, how many would we actually have? Now we could also take a look at the zeros, or in other words, those x-intercepts. A polynomial of degree n, okay, looking at that degree again, has at most n zeros or roots. And that's what the fundamental theorem of algebra told us in the last section, was that whatever our degree is, that's how many zeros or roots we should actually have. So again, looking at a little example here, maybe we'll look at x squared. That's telling us we have at most 2 zeros. Okay, now if we think about it graphically, we could have a quadratic that looks like this. We'll have our parabola, and notice how the zeros in that case would be right here and right here. So that is our at most 2 zeros. But we could have a parabola, for instance, that just sits on the x-axis. So in this case, we would just have 1. But notice how that still makes sense. We have at most 2 zeros. In this case, we would have 1 real zero, but we would also have 1 imaginary zero, I guess you could say. Or this is a double root. We would have 1 0 right there. But we could also have a quadratic that doesn't even touch the x-axis at all. So we don't have any real zeros, but we would have 2 imaginary, what we would say. So this is how many zeros or roots we should actually anticipate in our polynomial graph. So last but not least, we're going to use a function's multiplicity to help us graph these polynomials by hand. And this idea of multiplicity is probably the most important concept, I guess, or idea we can find in these polynomial graphs to help us, or polynomial equations, to help us graph them by hand. And a multiplicity, a factor's multiplicity, is the number of times the factor occurs within the polynomial. Literally, how many multiple times is it showing up? So for example, if we were to examine this function, okay, this polynomial graph, the factor x minus 3, this little guy right here, we would say has a multiplicity of 1. Because if you think about it, I know this is nice and neat, notice how it's kind of condensed, but if you were to expand it, okay, if we were to actually write x twice, or write this factor 5 times, or this factor 8 times, we would get this giant beast right here. So the multiplicity is simply how many times the factor occurs. So notice how this x minus 3, if we were to expand everything, is just showing up once, okay, somewhere right here. But that idea of it only showing up once was the actual exponent on that factor. So this factor is only showing up once because it just has that exponent of 1. But this factor of x minus 7, okay, this guy right here, would have a multiplicity of 8. Because again, if we were to expand it, we would have 1, 2, 3, 4, 5, 6, 7, 8 of those factors based on that exponent. So looking at the exponent of your polynomial equation when it's in factored form, okay, we have these factors, that's where we're getting this idea of multiplicity. How many times does that factor actually show up? And this idea of multiplicity, just like that end behavior we talked about, is telling us something about how the graph actually looks. If we have an even multiplicity, like this idea of, or multiplicity of 8 we had here on the x minus 7. We're going to take a look at that example right here. If we have an even multiplicity, the graph is tangent to the x-axis at that corresponding 0. Now tangent just meaning it just touches that x-axis. So for example, if we were to actually draw a picture, notice how if it's x minus 7, the 0 or x-intercept would be occurring at positive 7. So we would have something right there. And if it's just touching it, we might have something that looks like this. Maybe our polynomial graph would look like this. So it just touches it. It comes down, just touches it, but then it kind of bounces right back. That's what tangent means. It's just touching it at one particular point. But if we take a look at an odd multiplicity, like the x minus 3, notice how it only occurred once. Okay, that's an odd multiplicity. In this case, our graph actually crosses the x-axis at that corresponding 0. Or in other words, it's actually going through it. So if this factor is x minus 3, we know the 0, or x-intercept, is occurring at positive 3. And if the graph has to actually cross it or go through the x-axis, maybe in this case, our polynomial function is going to look something like this. It's actually going through that value, it's going through that x-intercept because this factor's multiplicity was odd. So depending on the multiplicity, if it's even or odd, we know what the graph should look like at that particular x-intercept. Is it just touching the x-intercept, or is it actually going through that x-intercept? Alright, so let's try to actually bring all of this information together. I know it's kind of a lot to take in at once, but let's try to bring all of it in together to help us graph this polynomial equation by hand. So the first thing we're going to do is try to analyze what's going on, and then once we analyze what's going on, we're going to transport that information onto our coordinate graph over here. So the first thing we're going to try to figure out is, this particular question is asking us, how does the graph behave with relation to the x-axis when x equals 2? So notice how this value, this x equals 2, is coming from this particular factor, because this answer of 2 is what would make this factor equal to 0. So this particular factor, notice how it has an even multiplicity. So if this 0, this x equals 2 answer, has an even multiplicity, what's actually going on the x-axis? Is it tangent to it? Is it just touching the x-axis at this point? Or is it actually going through the x-axis at this point? Well, an even multiplicity in this case of 2 would mean that our graph should be tangent to the x-axis when x equals 2. Tangent just meaning it just touches it. Now part B is asking us what are the real zeros of this function. So taking a look at our factored polynomial here, it looks like our first factor would give us a real 0 of -1. Our second factor here would give us a real 0 of positive 2. And our third factor here would give us a real 0 of 1. So if these are real zeros, if these are x-intercepts, we can most definitely plot those on our graph. So I'm just going to go ahead right now and plot those since I know that they should be on here. So we have -1, positive 2, and positive 1. Now let's take a look at this. What is the degree of the function? So I know it's in factored form right now, but if we were to expand it, if we were to multiply absolutely everything together, get it in standard form, what would that largest exponent be? But there's kind of a shortcut we can take a look at in this case. Notice how this x essentially has a degree of 1, because that's the exponent on this factor. So this exponent has a degree of 1, and we're multiplying it. Notice how we have parentheses here. We're multiplying it by this x that has a degree or exponent of 2. And we're also multiplying that, because we have more parentheses here, by this x that has an exponent of 3. So if we were to take x times x squared times x to the third, that would give us overall an x to the 6th. So in this case, if we were to expand everything, we could anticipate a degree of 6. After everything's all said and done, this x has a degree of 1, this x has a degree of 2, this x has a degree of 3. Overall, we have a degree of 6. Now using this degree, we want to describe the end behavior using limits. So the left end behavior, as our graph goes out towards -infinity all the way on this left side, what's actually going on? And as we go off to the right hand side all the way towards positive infinity, what's going on in that case? Now in terms of end behavior, we got to take a look at two things. We got to take a look at the leading coefficient. So in that case, our leading number is -2, but we also got to take a look at the degree. So in this case, our leading coefficient is negative, and our degree is 6. So even degree, negative leading coefficient, we could anticipate a graph that kind of looks like this. Okay, if you need to reference your chart from the beginning of the lesson, you can absolutely do that. But we're going to have these two end behaviors both going down. So on the left-hand side, we should have negative infinity, and on the right-hand side as well. So we're not really sure what's going on in the middle. We might have some humps and bumps, but we know most definitely on the left and the right-hand side, based on this even degree and negative leading coefficient, both end behaviors would be going down towards negative infinity. So with all this information, we want to sketch the graph. So it's all nice right now that we know that these are specific points on our graph. But now let's use the end behavior to help us out. We know definitely on the left-hand side, our graph should be going down. So right now, since this is my leftmost point, I'm going to draw an arrow that goes down. There is my left-hand side end behavior. Now this is my rightmost end behavior. So let's take our rightmost point and draw another end behavior that's going down. So again, we're not really sure what's going on in the middle. We might have some humps and bumps, but we most definitely know that on the left and right hand side, both pieces would be going down. Now to figure out what the humps and bumps actually look like, this is where we need to take a look at those multiplicities. So this 0 right here of -1 came from this factor of x plus 1, and notice how the multiplicity is odd. So that tells us that our graph actually goes through this point. So we're going to go through the point, and we know we have to connect it to this one, so I'm just going to draw it in that fashion. Now you can draw it higher, this is just a rough sketch, but we know we actually have to go through that point, so we're going to go through it and kind of connect it to the next dot. Now in this case, this is an x-intercept of 1, and that came from this factor. Notice how this factor's multiplicity is odd as well, so that means we have to cross it or go through it again. And then I'm going to connect it to my next point. Now this particular x-intercept is 2, which came from this factor, and notice how its multiplicity is even, so that means it's just touching it. It's tangent to it, it just touches it. So notice how when we connect it, we come up, but our end behavior brings us right back down. So we're just touching it, we're just touching our x-axis at that particular point. So you can kind of see everything that's going on here. We're going through this one because it has an odd multiplicity. We're going through this one because it also has an odd multiplicity. But notice how we're just touching the x value of 2 because it was even. Alright, so let's try one that's a little bit more difficult. Instead of having a polynomial equation that's already factored for us, this time we're actually going to have to factor it ourselves. So in this case, we're going to factor this polynomial and then sketch a graph by hand. So they give us some information. They tell us that f of -2 equals 0. So this is an x value that specifically gives us a y value of 0. If you want to think about it as an ordered pair, you can write it like that. But since this x value of -2 gives us a y value of 0, that means, remember when we did long division, that x plus 2 is a factor. Okay, it actually goes in evenly, because if we were to plug in -2 into our equation, we'd get an answer, or in other words, a remainder of 0. So we know that this x plus 2 is a factor of this equation. We can use this value, this -2, to help us factor it. So we're going to use, I like to use synthetic division. I think it's a little faster. So let's use this information and the synthetic division setup to help us factor it to find the other zeros. Now we got to be careful, because notice how we do have a nice progression of exponents, but we are missing that constant term, so we need to put in 0. We need that placeholder. So going through synthetic division, we'll drop the first number and then do our multiplications and additions from there. Let's see what we get. And it works out. So we get that remainder of 0 just like we thought. So with this quotient, we can anticipate an x to the 4th plus 4x to the 3rd minus 16x squared minus 64x. There we go. Alright, so if this is our quotient, that means it's a factor as well, because this -2 was a factor in our original. So not only is the -2 a factor, but so is our quotient is a factor as well. So let's try to factor this. Is there anything that we can initially maybe pull out? Maybe. So let's take out an x. They all have an x in common. And the next thing I notice right off the bat is that I have 4 terms. So I'm going to use factor by grouping to help us go just a little bit further. Alright, so I'm immediately going to put the x out here. I don't want to forget that. But then we got to take a look at, well, what can I take out of my first group? It looks like I can take out x squared. And I'm left with an x plus 4. But I want to take out something from my second group in order to match this piece. So I think that would be a -16. That way I can get an x plus 4. Alright, so I still have the x out front, didn't do anything with that. So my 2 factors when I do by grouping are the x squared minus 16, what I pulled out of both, and then the x plus 4 that matched. But we can take this piece a little bit further because it is a difference of squares. X squared started as an x, 16 is a perfect square, it started as a 4, and then one's plus, one's minus, they're conjugates of each other. So there we go. Alright, so our final factored, I'm going to rewrite this over here, f of x, so our original equation, we knew that x plus 2 is a factor, so I'm going to go ahead and write that. We found out that x is a factor, so since it's all by itself, I'm just going to put it out front. We also know that x plus 4 is a factor, but notice how that shows up twice. So we can write x plus 4 squared. And then we have the x minus 4 as well. So there is our polynomial in factored form. Notice how it looks very similar to the last example we did. So there might not be a time or a case where I give you a factored one. You might have to factor it yourself using that synthetic division to kind of help you through that process. So now that we have it in factored form, let's try to graph it by hand. So the first thing we're going to do is try to find our zeros, our x-intercepts. This x is giving us an x-intercept of 0. It's lonely. It's all by itself. This x is giving us a -2. This x is going to give us a -4. And this one is going to give us a +4. Now I also suggest right off the bat writing down the multiplicities. How many times does each one actually show up? Well, this x only shows up once. So that means 0 has a multiplicity of 1. This factor only shows up once. This factor shows up twice. And this factor only shows up once. Okay, we're looking at the exponents to kind of help us out in that case. So if these are the zeros, let's plot them on our graph. We can plot 0, we can plot -2, we can plot -4, as well as 1, 2, 3, as well as +4. So we absolutely know those are on our graph. Now let's try to figure out end behavior. So should I draw an arrow going up or down on the left-hand side? Should I draw an arrow going up or down on the right-hand side? What's actually going on? Well, in this case, we can actually take a look at our original equation. Okay, we're going to take a look at this guy right here. Notice how the leading coefficient is 1. Okay, so that's a positive number. And our degree is 5. So if we think about end behavior, odd degree, even leading coefficient, we could anticipate something that looks like this. So we're going to have an end behavior going down. We might have a few humps and bumps in the middle, but we would also have an end behavior going up on the right-hand side. So we can anticipate end behavior going down on the left, and then end behavior going up on the right. So that's what the first term is telling us in this case. Now notice how you could also get the same thing by looking at your factored form. This x has a degree of 1. This x has a degree of 1. This x has a degree of 2. And this x has a degree of 1. Kind of looking at our multiplicities here. And if we were to multiply all those together, we would eventually get x to the 5th, which is what we started with up here. So there are some different ways that you can take a look at that degree to find that in this case. Alright, so now let's try to figure out what are the humps and bumps doing in the middle. Well, this x value of -4 had an even multiplicity, so that means we just touched this point. So even though I'm touching it now, I don't want to actually go through it. That means my graph is going to be coming back down. So notice how we're just touching it at this point. So we're kind of going to play connect the dots and then just go to our next point. This one right here has an odd multiplicity, so we actually want to go through it. Again, playing connect the dots. This x-intercept has an odd multiplicity, so we're actually going to go through that as well. Playing connect the dots. And just to check, this x-intercept had an odd multiplicity as well. It had a multiplicity of 1. So notice how we're actually going through that one too. So just a rough sketch, we can anticipate something going down on the left, going up on the right, and we're going to have these turning points in the middle. We have this turning point, and this one, and this one, and this one. Alright, so what I want you to do is pause the video and try this one on your own. I'll be back in a little bit to see how you do. Alright, so let's check it out and see how we did. Based on the graph, we want to identify the following information. Part A wanted us to find those locals, or in other words, relative minimum values. So looking at our graph, it looks like we have one right here and right here. Those are some low points on our graph. So you could have listed those ordered pairs. Part B wanted the relative or local maximums. So those would be our relative high points. Those look like some right there, so you could have listed those ordered pairs as well. Now notice how part C is asking for the minimum degree, and that minimum degree actually depends on how many turning points, or in other words extrema, that you have. So we listed 1, 2, 3, 4 points, or 4 extrema. Okay, we had 2 minimums and 2 maximums, so that means we have 4 turning points. This is a turning point because it goes from increasing to decreasing, but this one is also a turning point because it goes from decreasing to increasing, specifically at that point. Same things going on in these two cases. So if we have 4 turning points in this particular graph, that means our minimum degree is 1 more than the number of turning points. So we would have at least a degree of 5. We could have 6, we could have 7, we could have 100, okay? But at least our minimum degree is 5 in this case. So with that information, as well as looking at this graph, we want to write a possible equation that would give us this graph. And in order to do that, we need to know those x-intercepts. So here is an x-intercept, here is an x-intercept, and here is one as well. Notice how those 3 points are on this x-axis. So this particular point is at -6, which means in our function we would need a factor of an x plus 6. So we can write that out. This x-intercept is 0, so we could just have an x all by itself. You could write plus 0 if you want to. Okay, not necessary, but you could. And this x-intercept is a positive 5, which means our factor in our equation would have to be an x minus 5. So that's how we're getting these factors based on these x-intercepts. But then we got to be careful about what's actually going on graphically at those points. Notice how at this x-intercept our graph is just touching it. It kind of bounces back. So if it's just touching this point, that means that this point's factor would have to need an even multiplicity. So this x plus 6 right here, the factor that came from that x-intercept, would need an exponent that is even. So I put down 2. Maybe you put down 4 or 6. You could put down 100 if you wanted to, but it has to be even based on the fact that it is bouncing back or just tangent at that point. Same thing's going on here. Notice how our graph is just touching the x-axis. It is tangent to the x-axis at this particular point. So we need another even exponent right here. I put down 4, you could put down 2, maybe 6, whatever your heart desires, but it has to be even. Now this x-intercept, notice how our graph is actually going through it, okay? It crosses the x-axis at this point. So that means we need an odd exponent. We need that odd multiplicity. I put down 3, you could put down 1, you could put down 7. Again, whatever your heart desires, as long as it's odd. So you got to really take a look at your graph to help you analyze it in order to write out a possible function. Alright, so last but not least, we're going to talk about Descartes' rule of signs. This little process we're going to go through hopefully kind of quickly helps us determine how many positive and negative real zeros we have on a graph. So for instance, if you were going to think about a coordinate plane, you don't have to write this down, but I just want you to kind of pay attention for a second. If you were to kind of think about a coordinate plane, this process is going to help us determine how many x-intercepts we have over here on the positive side of our x-axis and how many x-intercepts are we going to have over here on the negative side of our x-axis. So are we just going to have 2 x-intercepts that are positive and one that's negative? Maybe we'll have 3 x-intercepts that are negative and only 2 that are positive. So this process we're going to go through helps us determine how many x-intercepts we have on the left-hand or negative side of our graph as well as the right-hand positive side. Now, just a little math history for you guys here real quickly. René Descartes, the guy who kind of came up with this process, is a Frenchman from the 1600s. He was a philosopher, a writer, a mathematician. He actually came up with the phrase or said, I think, therefore I am. He came up with the Cartesian coordinate system, so you can thank him for allowing us to plot points on a graph. He's also the father of analytic geometry, so basically he's just kind of an overall genius. But this is his rule of signs. So in order to determine the number of positive real zeros or real x-intercepts, we want to look for the number of changes in sign of the coefficients of our original function. Now, to determine the number of negative real zeros we have, we want to go through the same process, but this time we're going to check out the function f of negative x. So we're going to take our original function f of x, but just plug in a negative x, kind of like what we did for those even and odd functions. We wanted to put in the opposite, or that negative x, to determine if we got the same function, the opposite function, or something completely different. Same thing kind of going on here. Now, something that's a little tricky about this is that these number of changes, okay, are good to know, but we could also have another option that's less than this by an even number, okay, even kind of meaning 2 in both cases. And this might make a little bit more sense when we go through the example, so let's just kind of dive right into that. So we're going to list the possible numbers of zeros for f in this particular table. I know, I'm sorry, I forgot to put in the extra table or grids for you. You should need 5. I think I only put in 4 for yours, but you'll see when we fill out this table why you only need 5, because we're actually going to eliminate some information. So just, I mean, you could write this in if you want to kind of extend it, or you can just wait to fill this in until the end. But overall, just kind of pay attention for a second. Alright, so let's find the number of positive real zeros. We're going to take a look at our original function, so that's this guy right here. And we want to focus on the number of changes in sign of the coefficients. So for instance, this first coefficient right here is positive. If I take a look at the next coefficient, it is negative, so that is a sign change. We go from a positive number to a negative number. If I take a look at this coefficient, it's negative, and if I take a look at the next one, it's positive, so that's a sign change as well. If I keep going, this one's positive and this one's negative, so there's another sign change. This one's negative and this one's negative, so that doesn't change. And this one's negative and this one's negative, so that doesn't change as well. So overall, we have 3 sign changes. Okay, we went from 1, 2, and 3. So the number of positive, if I can write this out, the number of positive zeros, we could have 3. So again, if you were to think about your x-axis for a second, we could have 3 dots over here. That's what this sign change is telling us. Or we could have less than this by 2, an even number. So 2 less than 3, okay, we could actually only have 1. But again, there's always that option that we could have none. So we're just going to keep subtracting 2. If we have like a really big number here, we could just keep subtracting 2, but we will always have that option of 0 because it may not touch the x-axis at all. So our original sign changes, in this case, is 3. Subtracting 2, we could have only 1, or we could have none. So this is just the positive. But now let's check out the negative. So now we want to take negative x and plug it into our original function. That's what I kind of did right here, so you can see the substitutions. And if we simplify, negative x to the 6 is just going to end up being a positive anyway, so this one doesn't really change. But negative x to the 5th is going to be a negative 1 coefficient, but we also have the negative 3 coefficient, so when we multiply those together, it ends up being positive. So if we would actually go through and simplify the substitutions of this negative x, we would get this final simplified function. So now let's check out the number of negative zeros we might possibly have. So how many are we going to have over here on the left-hand side? So taking a look at our sign changes, this coefficient is positive and this one's positive, so that's not a change. This one's positive and this one's positive, so that's not a change. This one's positive and this one's negative, okay, so that's definitely a change. This one's negative and this one's positive, so that one's a change as well. And this one's positive and our last one is negative, so there's another change. So again, we can have 3, okay, possibly 3, or 2 less than this, which would be 1, but we could also have none. Okay, we might not have any on the left-hand side. So we're going to use this information to determine how many zeros do we actually have, how many positives, how many negatives, how many imaginaries do we have, as well as the total zeros. Now we could also immediately fill out this column because based on our degree, okay, this little guy right here of 6, that's telling us we should have 6 total zeros, positive, negative, imaginary, doesn't really matter. We have 6 total regardless. So we could just simply fill all of these down here with 6. Alright, so here's the thing. We could have 3 positive real zeros. We could also have 3 negative real zeros. But that means that if we have 3 positive and 3 negative, that gives us our overall of 6. We might not have any imaginary. Now we could also have 3 positive real zeros, but maybe we only have 1 negative real zero. This is giving us 4 positive and negative, but we all need a total of 6, which means the number of imaginary we would have to be 2, because 3 plus 1 gives us 4. Oh, I'm sorry. Yeah, and then plus 2 would give us 6. So knowing this total is going to help us fill out this imaginary column. We could have 3 positive real zeros, but we could have 0. In that case, if we need a total of 6 and we already know we have 3 positive ones, that means we must have 3 imaginary. So if we continue the process, maybe we only have 1 positive and then 3 negative. That means we would need 2 imaginary. Maybe we only have 1 positive and 1 negative, which means we would need 4 imaginary. And maybe we only have 1 positive and no negatives, which means we would need 5 imaginary. So we're just going through all the different combinations of positive and negative real zeros to help us go through this chart. Last but not least, we might not have any positives, which means we could have 3 negatives. Consequently, we would need 3 imaginary. We could have no positives. We could have 1 negative, which means we would need 5 imaginary. And last but not least, we might not have any positives, we might not have any negatives, and the only zeros we have would be imaginary. So that means we have a total of 6. But here's the thing, okay, we don't need all of this information because we know imaginary zeros come in conjugate pairs. Okay, so imaginary zeros can only come in pairs, meaning an even number of imaginary zeros. And notice how in this case right here, we would need 3. But that means that we don't have pairs of imaginary zeros because we have an odd number of imaginary zeros. So this option right here will never ever happen because we're not going to have an even number of imaginary zeros. Neither is this one. So this option, okay, this possible combination of positive and negative real zeros will never happen either. And neither will this one. Kind of skipped one there for a second because we have an odd amount in imaginaries, and neither will this one as well. Okay, so we can kind of cross those out because we know those will never happen. We do not have an even number of imaginary zeros. So the only cases that we could possibly have for this function, we could have 3 positive and 3 negative. We could have 3 positive, 1 negative, 2 imaginary, 1 positive, 3 negative, 2 imaginary, 1 positive, 1 negative, 4 imaginary, or no positives, no negatives, and 6 imaginary. So we kind of got to go through all the different combinations and then eliminate the ones that don't make sense, okay, these odd number of imaginary zeros, to help us determine what could possibly happen, how many zeros could we have in this function. So I just want to thank you guys for going through this with me. I know this lesson was a little long. Good luck on the application and the practice, and most of all that mastery check without using a calculator. I know you guys will do great. I'll see you later.